everything that comes forward.
We also encourage them in various curricular and co-curricular activities through student forum activities.
Many of our students get opportunities to do internships at reputed international universities like TU Munich, KTH, MIT, Harvard University, etc. through student exchange program.
And we also have a placement class right from our second year. It's a CAR department, which is a dedicated department, and it teaches on the basis of aptitude, verbal skills, and soft skills.
Coming to my years in Amrita, it has been filled with memories and which I will cherish in my lifetime.
In Triple department, we have highly experienced and qualified faculty.
The Electrical and Electronics Engineering at Amrita has a credit-based curriculum and syllabus provides multidisciplinary academic excellence with special emphasis on core human values.
I am extremely proud to be a part of the Tripli department in Amrita because Tripli is one of the most oldest departments available and it is one of the most departments in which all other branches have evolved from.
Our course, especially in Tripoli, we have a very systematically programmed course where they teach us right from the basics and move on in a very organized manner so that we understand everything that comes forward.
We also encourage them in various curricular and co-curricular activities through student forum activities.
Many of our students get opportunities to do internships at reputed international universities like TU Munich, KTH, MIT, Harvard University, etc. through student exchange program.
And we also have a placement class right from our second year. It's a CAR department, which is a dedicated department, and it teaches on the basis of aptitude, verbal skills, and soft skills.
Coming to my years in Amrita, it has been filled with memories and which I will cherish in my lifetime.
In Triple department, we have highly experienced and qualified faculty.
The Electrical and Electronics Engineering at Amrita has a credit-based curriculum and syllabus provides multidisciplinary academic excellence with special emphasis on core human values.
I am extremely proud to be a part of the department because in which all other branches have evolved from.
Our course, especially in Tripoli, we have a very systematically programmed course where they teach us right from the basics and move on in a very organized manner so that we understand everything that comes forward.
We also encourage them in various curricular and co-curricular activities through student forum activities.
Many of our students get opportunities to do internships at reputed international universities like TU Munich, KTH, MIT, Harvard University, etc. through student exchange program.
Hello.
Hello, Rashmi ma'am. Can we start,
Yeah,
ma'am?
yes, ma'am.
Yes, ma'am. Okay.
Yeah.
Revant, share the other PPT, Dama. Yeah, ma'am.
Yes, ma'am. Good morning to one and all who are attending this webinar. Who are attending this panel discussion. I welcome you all for the panel discussion on applications of power electronics in engineering. We, the Department of Electrical and Electronics Engineering in Bangalore, we offer MTech in two specializations: power electronics and drives and embedded systems. Lot of our faculty are engaged in research. The major thrust areas where lot of research is going on is in the field of microgrid, power electronics and drives, embedded system, and applications of embedded system in the field of robotics. We have very well equipped lab infrastructure. We have DST funded power system research lab, wherein lot of work is going on integration of renewable energy sources to the grid. And we also have a lab on smart grid, which has been which has been funded by VGST, the government of Karnataka. Apart from that, we also have the Center for Robotics, wherein the students are encouraged to do the projects, in-house projects and robotics. All our MTech students and BTech students, they are encouraged to do in-house projects. Our curriculum is designed in such a way that we have almost all the courses integrated with the lab. Along with the theoretical designing aspects, our students will also get an opportunity to have more hands-on experience. Our electives will be designed in such a way that they will cater to the needs of industry so that we can bridge the gap between academia and industry. To name few, our MTech in power electronics and drives, it is structured in such a way that it covers the courses which will introduce system level modeling and analysis, design and integration of drives using power converters, integration of renewable energy resources to the grid, smart grid, and vehicles battery management for electric vehicles. And apart from that, our students will also have the exposure to modern digital signal processor and controllers, which are very much essential for digital control for any application. Therefore, they will be made to do the projects in all the courses which involves design, simulation, fabrication, and testing of all the power electronic system, which will have a research focus. Having been trained in that, our students will get placed in reputed companies. We also offer MTech in embedded systems, as I mentioned. The embedded system curriculum is structured such a way that it covers embedded system programming, signal and image processing, embedded processor architecture and design, RTOs, and state-of-the-art technologies like FPGA-based system design. And we also include advanced artificial intelligence techniques, machine learning, and application of embedded systems in robotics, smart grid, and automotive applications. Here also the students are encouraged to design, simulate, and then develop the prototypes. Having experience both in theory, having theoretical background and hands-on experience, our students get placed. To name few companies where our students get internship and placement opportunities are ABB, DRDO, CPRI, Honeywell, Robert Bosch, Opel RT, Bilva Infra, and so on. As I said, our students are encouraged to do research. Not only in MTech, they can pursue their MTech, they can continue their MTech work to PhD. We have integrated MTech PhD program. Few research areas to mention where our faculty are actively involved are power quality, STATCOM, hybrid fax controllers, electric drives, hybrid electric vehicles and battery management, design of power converters for various applications for space, aerospace and satellite applications, hybrid energy systems, energy management, portfolio optimization of electricity market modeling, and embedded controller for power electronic devices, smart devices using smart techniques, reconfigurable system design and implementation on FPGA or ASIC. So with this short note, I welcome you all for this panel discussion. Let me introduce the moderators moderator of today's web panel discussion, Dr. Kaushik Basu. Dr. Kaushik Basu is from Indian Institute of Science, Bengaluru. Dr. Kaushik works as assistant professor since July 2015. Earlier to this, Sir has served Dyna Power Company, LLC Electronics and Control, and prior to this, he was a graduate research assistant at University of Minnesota. Sir also has taught a course on transmission lines in the fields of waves to undergraduate students. He worked as instructors in the University of Minnesota for 8 months. So it is a great pleasure to invite you for this. I request you to introduce the speakers and I hand over the session to Dr. Kaushik. So please.
Good morning. So I thank Amrita for organizing such an interesting event and also giving me an opportunity to moderate this panel discussion. Uh, so, so in power electronics, basically, I am assuming that a lot of undergrads are today attending this session, and one of the objective is to motivate them to join the master's program at your university. So, so I'll briefly tell you about what is power electronics is about and what we are going to discuss today. So, in power electronics, basically we convert electric power from one form to another, DC to AC or AC to DC. So, a power electronic converter can be found between the supply or the utility grid and a load, like the charger of your phone, converting AC to DC, or between a source and the grid, like the solar inverter, converting DC to AC. A power electronic converter typically consists of a network of semiconductor switches like IGBTs and MOSFETs, along with lossless passives like inductors and capacitors. So it is truly an interdisciplinary area connecting diverse fields like semiconductor devices, analog and digital circuit design, embedded systems design, control theory, heat transfer, and you name it. It is estimated that within next decade, about 90% of electrical energy will be processed through some kind of power electronic converter while being transferred between source and the load.
Sir, excuse me.
Today, yeah.
Slides are not visible.
I don't have any slide. I don't have any slides. So, because I'm
Yes, sir, you can
presenting today,
continue, sir.
right? Yeah. So, uh, today we have an excellent panel of speakers who will enlighten us on the broad spectrum of the applications of power electronics, from electric transportation to harvesting energy from renewable sources to powering of large data centers. So, our first speaker is Dr. Swaminathan Ganeshan, Associate General Manager, Schneider Electric, Bengaluru. and I think he will be talking about power electronics in renewables. So here is a brief introduction about Dr. Swaminathan. So he is a project leader for product development with 19 years of experience in managing medium to large scale product development projects in power and energy and automation segments. Uh, he has experience Schneider Electric Associate General Manager R&D from June 2011 to present. Um, Bangalore successfully launched series of solar grid-tie inverters, 25 kilowatt to 125 kilowatt range, and IoT solutions for monitoring control of solar plants. He was an ABB project manager 2008 to 2011, successfully delivered products on time and budget, launched products in low voltage and medium voltage segment in international market and well received. Alstom he was in Alstom power conversion project manager, power generation from 2005 to 2008, and worked on static excitation systems and startup frequency converters, and executed projects for gas turbines in combined cycle power plants, commissioning medium voltage, low voltage drives for test benches, steel and glass industry, and other applications. He was he worked from 2003 to 2005 in Megatech Control Limited as a deputy manager for process and plant automation, manufacturing and execution systems, enterprise resource planning, airport logistics, and in-flight catering systems, material handling, vertical car parking systems. He did his PhD from VIT on energy management and performance improvement of microgrid from 10 to 18. And he did his MTech from the same institute in power electronics, graduated in 2004, and did his undergrad from Alagappa Chettiar College of Engineering and Technology and graduated in 2002. So it's a warm welcome to Dr. Ganesan.
Yeah, so it's a pleasure, Dr. Kaushik. Thanks for a very generous introduction. Let me share my screen. I hope my screen is visible to you all.
Yes.
Okay, thank you.
See. Thanks. Yeah.
So, so let me jump into the objective of this session. So before so we understand what is the need of power electronics in industry, at least a power and energy domain. So let us get an outlook like where we are and what we are looking at it. So I have so two data. One is on the energy, another one is on the electricity. So I hope you all know the difference between energy and electricity. So if you look at energy, so today, so we are at so 95,000 terawatt hour as per 2016 data. So so I have data from two agencies. One is International Energy Agency, another one is the Shell. So both have conducted energy survey globally and so come up with this figure. So so 95,000 terawatt hour energy as of 2016. So let us take some addition of 20% for another three to 4 years from 2016. So hello, can you continue? Okay, so in that you see so many source of energy like oil, that is fossil fuel, gas, renewables, and the heat, all that are there. When you look at the forecast in 20 years from now, it's growing from 95,000 to 133,000. Whereas in the case of another agency, it's 123. So let's not get into the accuracy of numbers, but what we are interested or what we should look at it is like the growth rate, the rate of growth from what it is today to what is going to be in another 20 years. So it's going to grow at a 40%, easily at 40% rate in terms of energy demand. Whereas if you look at electricity, like 20,000 terawatt hour of electricity, and that is going to grow by 35,000 and 43,000. So that is the again. So the interesting fact here is the percentage, the gap between what it is today and what is going to be in another 20 years. Okay, so the future is going to be, or it should be sustainable, and some more focused on renewable and decentralized power. So that is going to be. So you know the reason. Like so a few years back, so there was a global summit on climate, that is COP21. It happened in Paris. So every country signed a mandate to reduce their carbon footprint, uh, which means so we need to gradually reduce carbon emission and move towards renewable source of energy. So that will open up a huge uh, problem or opportunity in front of us to go in sustainable mode of energy. So today, if you see, like so our power generation is a kind of a centralized power generation. So we have power generation, like if you take Karnataka, so we have 4 or 5 places, the centralized generation plants are there. From there, so the electricity is transmitted over transmission line and taken up to the end user. So like a consumer. Like if I get energy at my home, since it's generated far off, like say 200, 300 kilometer away from my place. So that's a conventional energy setup. But in future, it's not going to be the same. So like everyone will be asked to take part in generation and consumption. So that we call it as a prosumer market. So today we are in consumer market with regards to energy industry. So it's going to become a prosumer market. So prosumer market is nothing but everyone will take part buying and selling. So today I buy electricity. I only buy electricity. So that is my role. So somebody is generating, I buy. Whereas in future, I buy at the same time I will sell also. So that is a prosumer market. So this renewable energy will enable that the prosumer centric market. So maybe in the following slide I will tell so how our opportunity, like that is so how power electronics engineer can see it as an opportunity. So I mentioned about the prosumer revolution. So this will enable access to energy for everyone. Like so recently in India we declared so the 100% electrification throughout the country. So how it was realized? It was realized through renewable. Because in many hilly terrain, it's difficult to take the transmission line, or it will call for huge infrastructure expenses. You need to set up, and it cannot happen immediately. Whereas the renewable will enable you to have access to energy in all location, like in far off location. It's easy to put up a solar panel and get access to electricity. Also, you can put some storage system as well that will ensure 24/7 electrical energy and reliable. So today, so what we get is so not highly reliable. Anytime power will go, we will not be notified in advance. That is the reliability we have. But going forward, it has to be more reliable, because more and more we are getting electrified. So it should be more reliable. So in terms of the fluctuation, voltage, frequency, everything, it should be reliable. So again, the reliability will not come. It will come with some cost, and also so the technology should also scale up to ensure that we are access to a reliable source of energy. And so the energy mix. So today, like for example, if you take one generation plant, either it will be a coal powered plant, or it will be gas powered plant, or it will be atomic power plant. But the future is not going to be the same. It's just we will have energy from all different sources, like say from solar, wind, biomass, and along with the conventional source of energies like coal, the thermal plant, atomic plant, and so on. So we are migrating from centralized ecosystem to decentralized ecosystem. How we are going decentralized? Because if I have a roof space, so say for example 2000 square feet of rooftop I can put up a plant for 5 kilowatt of solar inverter. So that imagine a scenario. I don't have 5 kilowatt consumption, but during my noon time, like that time the irradiation will be peak, I will generate 5 kilowatt. So that 5 kilowatt will be consumed, will not be consumed at within my premises. So I will start to sell. So I will sell whatever surplus I am generating. So that's how the distributed generation as well as the prosumer participation comes into place. Okay. So if we fail to adapt this change, so then the future of electricity or the energy industry is not. It will not meet our expectation, or it will not meet the demand. So the power conversion. So when it comes to power conversion, the power transmission plays a major role. Like for example, we have a inverter development. I hear a lot of echo. So so we have a R&D center in Bangalore, and so we do a lot of product development, like it's a solar inverter for off-grid, on-grid, even hybrid system. So we need a lot of power electronics engineers to realize this dream or this expectation or this situational demand. So since so we are going to see this industry will never see a decline, no matter how the country's economy or the situation. Like even today, we see a lot of the turbulence due to the health situation. But the energy industry is not going to see a decline. There is no looking back for the energy industry. It's always going to grow only. So so when it's going to grow, it opens up a lot of opportunity. So like we say no, like so need is a mother of invention. So today we are in a situation where we need to have we need to provide access to electricity for everyone, access to energy for every individual, and at the same time it has to be sustainable, it has to be green, and so on, highly reliable. So this many problems we have in front of us. So we need people, we need a human resource to solve all this problem and come up with a very robust and highly sophisticated product which can be commercialized. Like today, if you see, like 1.3 billion people are not having access to electricity. So again, this is old data, maybe 3-4 years old. The numbers slightly would have improved, but looking at the growth of population, the percentage may remain still the same. So in the next 30 years, so the energy consumption is going to grow by 50%, like 1.5 times it's going to grow. Whereas we are compelled to reduce the carbon emission by half. Means you need to increase the generation by 50%, but at the same time you need to reduce your carbon emission, carbon footprint by half. And also we have to be more efficient by 3 times. So this is the mandate in front of us. So you can imagine the problem. One side you have to grow, other side you have to increase your efficiency and reduce your carbon footprint. So this opens up huge opportunity for electrical engineers, in specific power electronics engineers, because it's all talks about energy. So the energy doesn't come from the sky. So we need to have a power electronics device which will convert one source of energy to another source of energy, and then it's available for end user. For example, if you take a solar panel, so like it's available. So, but without power electronic converter, it cannot be hooked to grid, or it cannot be connected to your load. Same with the wind. So, if you wind also, like you have a force, but that force has to be channelized properly so that you will have a proper converters in place, and then you will be able to connect to the grid. So I think with this, I would like to end my introduction. Maybe in the later part of the discussion, if you have any specific question, I'm happy to share my viewpoint. But the world is going to become more electric and more connected, because so the digital, the buzzword is digitization. So we are also getting access to digital energy. So that's when the prosumer, like I will know when is my generation is going to increase, when is my generation is going to be less, and consumption also. At the same time, I will have access to data to understand what is my consumption pattern, when my consumption is more, when it's less, so that I can schedule properly. Whatever I generate, I can consume myself. Like for example, I can quote one incident a few years back during a summer day in Germany. So like Germany is a country where who is going far ahead from other countries in terms of renewable energy, like to be specific, solar. So they reached a stage wherein like they started generating surplus electricity from solar, like some 20 gigawatt plus on a single day they produced on a summer day, which is way more than what is the demand at that point in time. So that's when they have come up with a regulation, like earlier, to encourage people to go solar. They incentivized the installation, that is the capital investment. So if you are putting up a solar plant, they gave a lot of, government gave a lot of subsidy, and the tax benefit, everything was provided so that everyone went to solar. But now they started discouraging, because they are getting surplus energy in their demand. How they are discouraging? They are not saying don't put up your plant. They are still asking everyone to put up their plant, but they are asking everyone to consume what they produce. So instead of selling to grid, you consume whatever you produce, you consume. So this is opening up another industry, another business model, like the storage. So whoever is generating, they started putting up a storage in their premises, so that when there is no demand within their premises, they store it, so that the same can be consumed when there is no solar production. So, so there is no looking back with regards to energy industry. So always, so the future is going to be very bright, and the opportunities are plenty. Problems are also plenty. The complexity also increasing. So the problem is in front of you. It's up to us to how we look at it, and uh, uh, connect with what we are passionate about. So thank you very much for the opportunity. Back to Kaushik, Doctor.
Thank you, Dr. Swaminathan. It's a very interesting introduction to today's problem. And we will come back to you and we'll summarize what you said. But now I would like to invite our next speaker. Um, uh, Mr. Vishal Anand, Principal Engineer, Bloom Energy Private Limited, Bengaluru. He will talk about power electronics and grid integration. Here is a brief bio of Vishal. So Vishal Anand AG received his BE degree from Bharatiya University, Coimbatore in 2001, and MS in engineering from Indian Institute of Science in 2005. He worked at Tata Motors Private Limited, Pune from June 2005 to November 2005 as a manager. And from uh, 2005 to 2006, he worked in APC, American Power Conversion, as a design engineer. And from 2006 to present day, he is with Bloom Energy, and with a brief stint at Delta Energy Systems in Germany in the year 2012. At Bloom, he was held multiple roles and currently working as a principal engineer, where he leads a team working on inverter projects. He is working towards his PhD at IISc. His primary areas of interest are in the modeling, control, and design of grid connected and standalone inverters, topology analysis, and control of resonant converters. He is the secretary of IEEE Power Electronics Society, Bangalore chapter. Warm welcome to Vishal. I'm handing it over to you.
Thanks, Dr. Kaushik, and thanks to Amrita College for organizing this event, where we are able to have a discussion on the future of power electronics and how engineers of today can play a role in the opportunities and the challenges coming up tomorrow. So let me just share my presentation.
So, Vishal, you have 15 minutes.
Okay. Is my screen visible?
Yes, yes, yes.
Okay, so let me just jump straight in. So just have a technology overview, and from there we can go on. So coming off from where Dr. Swaminathan Ganeshan was talking about, we are in the era of distributed power generation. So if you look at the slide here, computing went through from a centralized approach with the mainframes and all those heavy computing devices in 80s and 90s to individual desktop PCs, and there was a big change, revolutionary change. And the same we encountered in telephony also, where we went from a centralized model of exchanges to a distributed model today that we are all enjoying the benefits. So the future of energy, like what Dr. Swaminathan Ganeshan told, is going to go from a very centralized kind of power generation to a very distributed model. So this is what we think is going to be the evolution of energy. So let me introduce about Bloom Energy. So Bloom Energy is a distributed power generation company where we are doing power generation on site using fuel cells. So we take natural gas input and then we generate electricity on site. And it's fast time to power installed in months and delivers 24/7 on site power. And we also have mission critical reliability and also has a modular fault tolerant architecture. And there's also hardly any downtime for maintenance. So this is our product. So this is one installation of our product that we have done at Morgan Stanley in Times Square. So this is on a rooftop installation of a 750 kilowatt installation. So this is a typical modular DC fuel cell system architecture. So basically, our company generates power from fuel cells, and so I'll just give a brief of how the fuel cell basically looks like and what are the different components of fuel cell. So we have a fuel cell, primary fuel cell that takes gas input, and then it generates electricity, and this electricity is being so this is a very sloppy electricity. So this needs to be conditioned by power electronic converters. So the grid integration, even before we get into grid integration of this power, we need to first condition the power. And so this is also another area of application where we have DC to DC converters here that condition the power coming out of a fuel cell. And we also have a lot of electronics that goes into the product to look at the voltages and look at the temperatures. And of course, we have what is called as the BOP, or the balance of plant. So the balance of plant is the rest of the industrial plant where it looks at all the blowers, the sensors, the mass flow controllers, since it involves a lot of gas. So all this is packaged into a system which does the distributed process control. And since we are handling gas, which is combustible in nature, so we also needs to have a lot of safety controls in the entire system. So this is how a typical modular DC fuel cell system is going to look like. And once we have the DC power, so this is a system configuration where we have one set of DC coming out, and many of such DC outputs are parallel to generate a big DC bus. And also we have a centralized fuel process control. And finally, this DC power is input to inverters. So inverters are devices that converts regulated DC into variable AC. And these inverters feed the power either into the grid or into the load, depending on the end customer. So as I explained about the safety of an individual DC system, we also need to have the safety of the entire system, where we look at the different safety aspects like communications. Since we are looking at gas, we also look at temperatures. And in case of any safety events, we shut down system and have a maintenance schedule. So this is how a typical fuel cell system will look like inside. And looking at the system operation, so on the left we have the fuel cell that is generating DC, and it's a very a sloppy DC. Like once you start loading the fuel cell, you start drawing more and more current. The voltage kind of droops and it's not very stable. So this kind of unstable DC is not really what loads like. So we introduce a DC to DC converter that converts this sloppy DC into a stable DC. Like the individual DC-DC modules that I showed you, they convert the DC and make it a stiff DC. And this stiff DC is in turn provided to the inverter. So inverter is a device that converts a stable DC into variable frequency, variable voltage AC with sophisticated control. So this is how the entire system looks from the inside. So So this is how Bloom is enabling energy integration. So this is our the basic building block, that is the Bloom Energy Server. So we take different kinds of inputs. Basically, it could be natural gas or biogas or from landfill. So any of these inputs we take in.
Hello.
Hello.
Excuse
Okay.
me.
Yeah. Hello.
Yeah.
Hello.
Is there a question?
Excuse me, sir.
Yeah.
Yes. Yes.
Hello.
May I know who is this? Can you introduce? Hello. Hello. Okay, Vishwa, go ahead.
Okay. So the DC that is generated from a system is captured into a common generalized bus, and this bus we can integrate other sources of inputs like third-party solar, wind, or any other source through an auxiliary DC module and into the common bus. Or we also have storage modules that are built around batteries or ultracapacitors that is used for energy storage and buffering. And this is on the input side. On the output side, depending on the end application, we have different kinds of interfaces that we generally use. We generally go in for a grid-tied AC output for the grid integration application that I'm going to explain further. Or if the requirement of the customer is uninterrupted AC kind of a UPS level quality output, then we use the load interface or the UPM. And if certain cases where they just need a DC output, we can go in for a electric vehicle charging kind of application. So the end applications are limitless based on only what the customer needs. We enable different kinds of energy integration. So that is about the technology that we're working on now. Let's look at a little more detail on the grid parallel system. So that one particular application that I want to focus on today. So this is a typical application of a grid parallel fuel cell system where we have the fuel cell system along with the inverter that is tied to a generalized grid. And we have, so this is installed particularly at the end user facility where the loads are there locally as shown here. And since this is a grid tied output, so whenever the grid is not available, even though if the gas is available, we can still not power the load because the grid is not available. So to work around those solutions, we have a DG set in the customer location. And when the grid is not available, the customer generally turns on the DG. So the fuel cell system can operate in parallel with the DG to reduce the load on the DG and thus reduce the diesel consumption. Anybody you would not like to want to use DG because the exhaust is really bad and it's very noisy. The fuel cell system, on the contrary, is there's no emissions and or very less emissions and there's no moving parts inside. So any day you would prefer this. So in the grid parallel operation, when the grid is present, so if it's a 4 megawatt load and our installation is about 2 megawatt, so 2 megawatts of power is generated from the fuel cell input to the gas and feeds the load. And the remaining power that is required by the load is supported by the grid. And the 4 megawatts generator is on standby. So suppose we, due to some maintenance or some activity, or we lose the grid. And so immediately the load loses its 4 megawatt input. And these are okay for loads that don't need a mission critical kind of output. What I mean by mission critical is kind of a data center or very critical care like hospitals and installations that can't be don't have any downtime. So if those kind of loads are there, then we wouldn't suggest this kind of output where you go in for a UPM or uninterrupted kind of output. However, when the load is okay, like for example, it's a store or another application, heating and lighting loads that don't need to be continuously on, so then loses the power. And now the fuel cell disconnects from the grid within a time of about 0.16 to 2 seconds. And the load will not see any voltage during this blackout time. And now once the DG senses that there's no voltage, then the DG starts. And typically the DG start time is about 60 to 180 seconds. And once the DG starts and the grid is available, the fuel cell system senses this and it starts powering back again and it starts delivering the load. That way, 2 megawatts of load is reduced on the DG, and thus we are reducing the emissions and the fuel consumption. So that is about the system application. Now let's look at a little bit more deeper into the grid tie inverter. So the inverter is the basic part of the system that is going to tie to the grid and generate the power that is required from the fuel cell into the grid. So what are the basic functions? So basically the inverter needs to generate variable frequency, variable amplitude, sinusoidal output voltage, and needs to continuously monitor the voltage and frequency of the grid and disconnect if the conditions are not within the specified limits, like the earlier case that I showed you. And needs to synchronize with the grid phase and frequency to ensure the maximum power output. And also it needs to adjust the phase of the current based on the requirements coming in terms of power factor. And also finally it needs to detect island formations. I'll briefly touch about these aspects. So on the left we have the topology of the grid tie inverter. So this is called neutral point clamp topology. It's a 3-level topology, and so basically power electronics goes into the heart of the inverter, where all these IGBTs and MOSFETs, like what Dr. Kaushik was telling, needs to be designed, and all the drive circuits, the choice of the passive components, and everything, entire thing is all power electronics only. So the control of the grid tie inverter ensures that we are able to generate a particular voltage here that will give the required current into the grid. And using a phase lock loop, we synchronize our current to the voltage phase of the voltage. And we also keep continuously monitoring the voltage for amplitude and frequency. And now let's looking at the utility interaction. So since we are feeding power into the utility, so the grid tie inverter must always keep looking at the voltage and frequency and ensure that they are within the required limits. Each country have their own grid standards, and it's imperative that the particular inverter follows the country's grid code. The Indian grid code is available here, and these are the different codes of the different countries and what are the requirements in terms of the voltage, the frequency, and power factor. And so there's a lot of importance of the grid standards. They ensure that the inverters operate safe, and also it comply to all the other hazards, and there are no hazards operating the inverter. I just keep this. So one important factor of grid connection is the power factor. So what is power factor? So power factor is nothing but the ratio of the actual power and to the value of the RMS voltage and current. So the difference between the two is caused by the reactance in the circuit and represents the power that does not do any useful work. So, but we need to control the power factor in grid tie inverters. How we control that is with the current command, the phase of the current command with respect to the voltage. So very classic example that you find in Wikipedia is the cost is an example of the beer. So where the beer content is actual real power that you actually consume, and the foam represents the reactive power which you don't consume, but finally you pay for that. So this is about power factor. So why is it important? So this is an example of the power factor, how it impacts the tariffs. So this is a building load. For example, if you see that normal, all the building loads will usually be reactive in nature. So you can see the current here that is reactive. And the distributed energy resource, in this case, fuel cell, it could be solar, it could be wind, anything. But most of the distributed energy resource always generate power in phase with the voltage. So what this ends up is all the real power consumed by the load is supported by the distributed energy resource, whereas the utility ends up doing all the dirty work and supports the reactive power. The problem with this is that the utility doesn't like this because they don't get to bill anything for this by the customer, and it requires the DER to support the reactive power. So this is very important. So the last topic I want to discuss today is on the islanding. So because we have more distributed energy resources, so what is islanding? So islanding refers to the condition in which the main grid is lost, but the grid tie inverter is looking at the reflection of its own voltage on the load as actual grid and continuous powering. So this is not acceptable because somebody might be thinking that the grid is not available, but actually the grid might be live. So the inverters have to know this and detect themselves, disconnect themselves. There are different techniques available. So one is called the passive islanding, where we look at the voltage and frequency, voltage levels, and then we disconnect. So this is a typical table given here for a grid. And the clearing time is the time for which the inverter ceases, looks at the voltage and disconnects. And all these settings must be adjustable. And this for the voltage. And we have a similar kind of table for the frequency, where we look at the frequency and disconnect. And finally, we also have active islanding methods, where the voltage and frequency might be within the voltage acceptable ranges. In such a case, the grid tie inverter must be able to detect the island formation using some active islanding methods and disconnect. So we use reactive power perturbation, and this is a simple technique that is used here. And for example, once in every, and this has to happen within 2 seconds. So once in every quarter mil or 250 millisecond, we keep perturbing the reactive current, and we look for variations in the frequency and disconnect. So this is a brief presentation that I had. So now we'll continue the discussion in the remaining talk, and now I hand it over back to you, Kaushik. And thanks to Amrita for again giving me the opportunity.
Thank you very much, Vishal, for this interesting presentation. We'll come back to you with questions. And now I would like to invite our next speaker, Mr. Saravanan Brahmanandam, who is a lead traction control system engineer in Alstom Transport India Limited. So, Sarvanan did his ME in Power Electronics and Drives from Government College of Technology, I think it is CET Coimbatore in 2005. And he has overall 15 years of experience in the area of power electronics and drives, with 11 plus years in the domain of traction, power electronics and control, which includes power converter design, development, digital control systems design with DSP and FPGA, component selection, semiconductor device loss computation, cooling system design and commissioning. So I would like to welcome, very warm welcome, Mr. Sarvanan.
Yes, sir. Thank you, Dr. Kaushik.
And,
yeah.
And you will be talking about today on power electronics and traction, right?
Yes. Yes.
Thank you. Thank you.
Thank you, Dr. Kaushik, and thank you, Amrita, for this opportunity to take up just a brief introduction on the power application of power electronics in engineering in the traction-based domain. So sorry for that. Can anyone make me as the meeting organizer or presenter can share, because it is not getting highlighted for me to present the screen? Yes, thank you. Thank you. It's now up. It's now done. It's now done. Thank you. Yes.
So, Sarvanan, you have 15 minutes.
Yes, please. Yes, sure.
Thank you. Thank you.
Okay, can you let me know once you're able to see the screen in the presentation mode?
Don't see it yet.
Yes, sir. Yes, it's able to see? Perfect. It's not there? Or since I have some glitches in my...
Somehow I can't see yet.
Is it not there, visible? I'm not sure because of some... Let me know.
Yes, sir. Yeah.
Perfect. Because there is some, again, the glitches that I was not a presenter, and then I just got the approval again to do it. Okay, thank you, Amrita, and thank you, Dr. Kaushik, for the intro, and Amrita for the giving me this opportunity to break up the call on power electronic instruction application. So just I want to introduce that power electronic instruction is very challenging and very challenging environment, vibration and shock and all of the stuff. At present, in the slide, what I'm showing you here, what is power electronics traction in Indian Railways, actually. So right from diesel electric propulsion, pure electric propulsion, and electric multiple unit. So all power electronics plays a role, right from diesel electric. So we have the diesel electric, where the diesel engine runs the system and the alternator produces the voltage, and you have the power conversion there to drive the motors. So that is on the diesel electric. So coming back to diesel electric propulsion, very purely electric propulsion, where you have the pantograph and you have the pure high voltage is above the electrification lines. That is nothing but 25 kV AC, where you get the 25 kV AC step down into the traction transformer, and after traction transformer you play the role of the power electronics, right from all these requirements, right from the jerk, right from the efficient utilization of power and all other stuff. So, and coming back to the third topic is more on the electric multiple unit. It's more than like EMUs. Hope you would have seen in all metropolitan cities. So where you have the distributed power, that is nothing but the power electronic is distributed all along the train. So these are all the three areas in Indian Railways. We have the electric propulsion based for the power electronic applications, where you drive the workhorse of the Indian Railways. So just to know glimpses how it works on high speed trains. For example, in Alstom we have started high speed trains from 1960s. So that is all the first generation, where you can see here it is approximately 260 and 300. What is 260 is nothing but the maximum commercial speed, and the 300 is the test speed. So all the first generation is based on thyristor based phase angle control system, and then they moved into the second generation in early 80s, where you work on GTOs based and the what oil cooled system. The third generation is IGBT based, and more pivoted towards the induction motors, and all your first generation is more related to the DC motor with the phase angle control. And the fourth generation is the one which is the latest one, which has the permanent magnet machines and the water cooled IGBT converters, where you can reach go up to 360 km/h. As of an Alstom, we have the world record of 574.8 on km/h. That is called V150. V150 in the sense velocity 150 meter per second. So where you drive the system at 150 meter per second, and that is based on the frictional one. I'm not talking on the maglev concept. So it is based on the frictional one. We have the world record. All these things are possible with power electronics. So let us go one by one. So how the normal locomotive works. This is the schematic of a normal locomotive, where you can see the four quadrant converter. What is nothing but the AC to DC conversion, where you does all the requirements right from harmonic suppression, AC to DC, your stable DC link voltage. It acts as a statcom, it acts as a harmonic suppressor, it acts as the reactive power compensation. All the things are done by this system. So where we have the challenge, I can explain you the challenge in the upcoming panel discussions. And you have the tuned filter circuit in the DC link, and you have the brake chopper. Chopper is nothing but DC to DC buck converter, where you want to stop the train when the regeneration is not possible. So next you come across the three-phase inverters individually controlling motors. What is this now? So where the power electronics, we have the challenge is that we have to run the train at 75-degree ambient temperature. For your information, in the Indian Railways, if you see the machine room inside the locomotive, you need to run. So there comes the challenges. So we have ambient temperature challenges, we have vibration and shock challenges, very high requirement on the power electronics with respect to power system. As Vishal and Dr. Swaminathan are telling, they are generation of power, but we need to take quality power from the grid and deliver the quantitative requirement to the motor. So there comes the power electronics, right from quality input and a productive output onto the motors. So this is the how the view of a traction converter on IGBT base looks like. Next, I'm just going to give a small glimpses on the high-speed train general architecture. What is high-speed train general architecture is mostly the individual motor is converted by an individual power station. Like our, if you say in our system, we have a individual transformer winding is going to drive the motor. What it does. So here the advantage is that we can have a better control on the motor, right from slip slide, motor level protections, and individual vector controls and DTC based system. So here you have the inverter, and the same converter does the same operation what I explicitly tell. And you can see here there is two type of winding. In Europe, the power electronic plays a vital role from one, for example, you were traveling from Portugal to Moscow or Lisbon to Moscow, you need to cross all the voltage levels, right from 25 kV, 15 kV in Germany, and then 3 kV in Belgium and 1.5 kV in Austria. So all these things are connected here. So you can have different catenary voltage. For example, you have 25 kV, it's in the black colored line, and you can see that 15 kV is on the red envelope. So what is the power electronic does? Power electronics plays a role that it plays with the voltages and gives the quality output or the requirement on the motor side. So there comes the challenges on the environment challenges, catenary challenges, and the catenary voltage variation challenges, and all these things are basically on the power electronics hardware and the control. So this how it looks like on the high speed trains. The one what I showed you is more on the locomotive base frame. So here it's more on the high speed trains, and you can see here you have a lot many traction converters cases connected distributedly. So in high speed, the power is distributed. In locomotive, its power is concentrated. And I'm coming back to the power electronic building block. We call as what is called as a heart of the system. What is power electronic building block? You know, the power electronic building block, the one which converts AC to DC, DC to DC, or AC to AC. It depends on how you use the configuration. So in IGBT based, we have the gate driver integrated inside the power electronic block. All are liquid cooled system, challenging ambient temperature, and compact system with high power density and auxiliary cool for the power electronic converter. So this is how the IGBT, it is 6.5 kV device and 750 ampere system. And you can see how our power building block looks like. So this is the block itself is an intelligent. It has its own DSP. It has its own FPGA where you have the control on the devices. It's not, you're not going to control the power flow here. The power electronic building block controls its own nature. Own nature in the sense it controls its own devices so that the device reliability is maintained. And it is also intelligent to estimate the junction temperature and tell to the next level of control. So this is how it looks like. You can see here, this is the one, the laser pointer. This is your hydraulic interface, and these are all your power interface. This is your DC interface, and this is your AC output. So the power electronics has its own level on control on also the power module lifetime estimation. For example, as I told you, I want to start the power traction or start the system at 75 degree ampere. I should not run the system more. Yes, sorry, I'm getting an echo. So the power electronic building block has its own intelligence, right from FPGAs, DSPs integrated into the system to make a more reliable and more robust power electronic building block for the challenging environment. Going back to the next era of power electronics. Now we called about IGBT. We started with GTO thyristors, we went into GTOs, and now we are going into IGBTs. Now IGBT is getting obsolete now. Another 5 years down the line, IGBT will be replaced by SiC MOSFET. What is SiC MOSFET? And what are all the different type of topologies in railway applications? That is nothing but right from 3-level DC to DC converters. That is nothing for DC catenary application, and medium frequency transformer based AC systems to have the reduced size of the power electronic converter, harmonic suppressors, and a system called as a AC to DC converters, and different PWM strategies for the motor control. And now these are all the different topologies. Now the SiC and GaN are going to play a very important role on the power electronic applications, where the SiC is going to have the natural cooled systems for power electronics when you want to drive the train, and GaN, that is a gallium nitride systems, are targeted for auxiliary converters with high switching frequency of approximately in terms of kilohertz of 100 kilohertz. That is already done in our Alstom point. And for your information, the SiC based systems are now deployed in very high ambient temperature like Dubai, where you play with the SiC advantage and the performance. So these are all the these are the evolution of power electronics in the upcoming years of 5 years down the line. So this is on the point where the physics of power electronics going to play the role. Next, as I told you, there are a new concept coming up. So you can see here, this is an AC catenary and you have a 50 hertz transformer. Now you remove the 50 hertz transformer, directly connect the AC 25 kV on to the IGBT. So how it is possible? It's through the series connection of your devices called cell. So you can see here, the 25 kV is connected, called as a series resonant converters. And this is called as a direct conversion of AC into medium frequency AC and then to DC. And you have the other topologies, where you have an intermediate DC link and you convert back to a medium frequency AC. See, these are all the two topologies upcoming, and now the lot of R&Ds and the series of papers are getting published in APEC and all other conferences. Now we are going towards on the reliability. As the number of IGBT increases, the reliability comes down. So we are seriously we are working around back what is the best we can do, what is the protection level we can have it on the device, on the explicitly having reliability. Reliability is it's a very fundamental point of traction. For example, if we start from here, we reach 4.5 hours to Chennai from Bangalore. So there comes the reliability. There comes, for example, if you're traveling from Brussels to UK, it's 2.5 hours journey. Everything depends on the RAMs, that the reliability, availability, maintainability, and the safety. So we are working strively on the power electronic architecture to make more reliable power electronic building block and the controls, so that we make a very efficient power conversion and the very efficient movement of people, because the one power station locomotive is approximately 4.5 megawatt. It is approximately 6,000 HP. It's a moving power station. So the reliability is our more prime importance, where we work a lot and we have the issues faced, and we can discuss on the points in our panel discussion session. Coming back to the last topic on the power electronics control, where it's a very interesting topic. We work a lot on this area. It's nothing but DSP and FPGA plays a very important role, right from system control layer till the PEB hardware control layer. For the system control layer, we have the level of inputs from the system or from the operational control center. Example, I can tell you, as I already told you, the power electronic converter can act as the way you want. For example, this is a moving power station where you can demand the locomotive, I need to draw reactive power, I need to draw active power, I need to draw lagging active power, I need to draw reactive active power. All these things are possible in this layer. And you have the converter control layer. You work more on the requirements on the level of DC link voltage and stuff to maintain this DC link voltage. Next is the PWM modulator and the switching layer. So you can do the harmonic estimation, selective harmonic elimination, torque ripple minimization, all these things on this layer. And next comes, as I already told you in my previous slide, on the PEB hardware layer. The PEB hardware itself has its own FPGAs and the DSPs to monitor the lifetime or the estimation of junction temperature of the IGBTs. So where we have a more reliable system, more new topologies we are planning to take, and more new innovations to work on the power electronics to make more reliable system. So there comes my session, and then we can take it forward for the next discussions, what is done and what are all the interesting points I happen. Explicitly, I can tell you how power electronic works. In an example in Europe, I can tell you, Europe, you have a frosting ice on the catenary. So you can make one power electronic converter to draw reactive power, other power electronic to converter to draw active power, so as to melt the ice and to move the train. So this is also an explicit requirement from the from the external level to drive the power electronics onto the point of applications and to the point of enhancement, and to the new era of power electronics is going to play the role in traction. So that are all we have a very vital topic on controlling a 100 kilohertz component with a FPGA. So that is also we are striving, working, a lot of R&D is going on. So power electronics has a wide scope on traction background, especially. So where we are now deployed, therefore. So thank you, Dr. Kaushik, for my intro, and Amrita for this opportunity. And we can take up in the next panel discussion session. Over to Kaushik. Thank you.
Thank you, Sarvanan, for this exciting talk. And we'll get back to you with more questions.
Yes.
And now I would like to call Mr. Bhaskar Reddy in. He is a technical specialist for electrification of smart power at ABB Bengaluru. He is presently working in ABB as a technical specialist with a total of 18 years of experience in design and development of mission critical power solutions for large data centers, with deep knowledge in data center power trends, power electronic topologies, embedded software and hardware, And he led teams in developing products such as digital static transfer switches, industrial UPS, modular UPS, grid-tied inverters, PCC switches, and power distribution and power quality monitoring products. I would like to welcome Mr. Bhaskar to give his talk on power electronics in data centers. Mr. Bhaskar Reddy, are you here?
Yeah, thank you, Kaushik. Can you hear me?
Yeah, please.
Yeah, sure. Okay. Thank you, Kaushik, and thank you, Amrita, for providing this opportunity for this panel discussion, wherein we can encourage the the students to get into higher studies in the areas of power electronics. So let me share my screen. Yeah, just let me know if you can see my screen.
Yes, sir.
Okay, so for me, the topic is today to discuss on the power electronics in data centers. So let's get into the straight away jump into the details. Yeah, I think let's first understand what are data centers. I think in today's world, I think every one of us is generating gigabytes of data. Each person, I think whether it's your photos or your emails or your files. So each of us generating huge amounts of data, and also whether it's even it could be related to your personal data or the data that you're trying to watch on, let's say, Netflix, YouTube. Yeah. So each one of us is generating data, and where does this all this data get saved? So I think nowadays we stopped using our own personal storage devices, but I think then all this data has to be stored somewhere. So the data centers are the places where this all the data from users is stored, and also there is a provision to process or transport the data to different connected devices. If you see the trend, I think even though the population is at around 7 billion or 8 billion for the world, but the number of devices connected to the internet are going billions every year, and I think they may reach. I think they are going to reach 50 billion this year. That means too many devices connected and too much data is getting generated, and they are coming into the data center. And the new technologies like digital transformation, IoT, Industry 4.0, big data, 5G technologies, all these developments which are happening now, they are going to put a lot of I think they may need that needs a lot of data centers to be available to store or process this data. So that means the evolution of data centers indirectly will cause the evolution of the power requirements for the data center. So they're huge. So I think currently the data centers, they're consuming around 3% of global energy. I think in coming few years, I think by 2025, it may reach 20% of our total energy production on Earth. That means it's going to be 1/5 of the energy which is generated on the Earth will be consumed by data centers. So knowing by these facts, if you see the typical data center elements, so I think there will be hardly, I think this will also provide you the amounts of data and then I think the importance of the data centers. So if you take a typical data center, there will be three parts. I think one is the power, the next is the cooling, and third one is your IT infrastructure. So because we are onto the power today, so we are more interested on what is the power requirements of a data center. So it's not just, I think not only, I think if we look from the power point of view, apart from power electronics, there are many areas within the data center which are in and around the electricity, power or storage. So there are many electrical products, and I think many of those have the power electronics inside them. So there are if you see the air and gas insulated switchgear, there are transformers. I think there are transfer switches. There are UPSs, there are switchboards, breakers, power distribution units, remote power panels. So these are all part of your electric distributions. The one critical point of the data centers is the continuous availability of the power. It's mission critical because I think if the power is down, I think that may create huge unavailability of these servers. So the intention of providing the continuous power leads to a lot of power conversions and storage and making the data, making the power available to all these servers which is within the data center. So let's get into the details. I think we can discuss all other products which are into this one, but let's focus to make the continuous availability of power. What are the typical components inside the data center? So to make, I think as other panel speakers were talking about, the main ingredients of this to make the critical power is the UPSs, static transfer switches, PDUs, and RPPs. So these devices will take right from the utility, from the generators to the UPS, then from there static switch. So each step in this flow makes the power availability, it gets multiplied. By the time it reaches the servers, the MTBF reaches very high, wherein I think you need to get into a situation where it's kind of no point of failures. So then let's get into the details of UPS. I think most of you might have heard as part of your academics what is typical UPS consists of. I think as mentioned by other speakers, it's I think the basic power electronic building blocks, they're also part of a UPS. Basically, you need to have a DC-DC, AC to DC converter, which takes the raw power. It could be from the utility or it could be from the generator, which is coming into the UPS. It converts to DC. And that DC, either it is stored onto the batteries or any storage devices. And from the DC-DC, then again, it's converted back to DC to AC, which is again distributed. And downstream, there are also static switches. They further expand the mission criticality of this power supply, where they'll be monitoring multiple UPS inputs and deliver the power to the loads. So what we look at, like say, to improve this continuous availability, to increase the uptime of these devices. So what do we do? So I think we need to do, I think we have to introduce the paralleling architectures. These have to be modular, and each module of this power electronic block has to have all the essential components which make the power availability high. And also, so you cannot switch off the data, having the UPS to make maybe service or something. So we should be able to have online swappable modules, so to ensure that there is a continuous uptime. So this means these are hot pluggable, hot swappable, and also something if you want to upgrade the firmware of these devices should be upgradable when they are online. And also we should be able to provide easy and controlling and monitoring of these devices so that we can keep them continuously running. And also we have to ensure that the service times are minimal when they want to completely put the data center to avoid any downtimes for the data centers. Okay, and of course there are different topologies available. I think maybe we will not go through all the details, but typically there are the modular designs wherein there is you can say a vertical and horizontal scalability of UPSs, or only horizontal scalability of UPSs. So in vertical you have modules embedded into the UPS. Maybe it starts from like say 10 kVA, 20 kVA, but 200 kVA of each modular device, and the total power it can go up to let's say 3.8 or 4 megawatt for all the UPS. And in horizontal also, the scalability, they start from I think 120 kilowatt, and they will go up to say up to 3.8 or 4 megawatt of the power. And typically, if you see data center power ranges, I think in the range of they start at megawatt range, but it will go up to 500 megawatt total power consumption within the devices. And you may think that most of the products are available, and what is your future? I think about what we are still need to do. These are some protection devices inside the data center. And what are the areas of innovation inside the data center or inside these power converters that we have in the data center? So there are, I think there are areas. We can, I think, if you see the efficiency or the PUE efficiency, the research is still going on. It's not like, though the present UPSs, they have reached almost 94-95% of the efficiency in the conversion. But still, the teams are working and the researchers are going on, whether it's a switching device or whether it's the methods of cooling or methods of identifying where the power loss are occurring. So there are innovations still happening in the areas of to improve the efficiency and reduce the losses. There are innovations in the topologies, innovations in the way the UPS are connected, in the way the transformers are integrated, the way the cables and joints are handled. So the innovations are still going on there. So this is the area that our new generations have to keep working on. And typically for the data center power, the typical measure is the PUE. So it's called the total efficiency by the IT energy. That means end of the day, the data center, the power has to be utilized by the IT infrastructure, that is your servers. So to deliver the power, how much energy we are wasting and how much energy we are actually consuming at the input side. So in the transformation, like whether it's in the UPS or whether it's in the storage or whether it's in the transformer, whether it's in the cables, how much energy we are losing. So our goal is to reduce the losses as much as possible and increase the work towards the betterment of PUE. And also we are working on the solutions in the area of measure, monitor and manage to again increase the efficiency. And also one of the challenges that we are looking at is the power density requirements are increasing day by day, because each rack, I think your server power, I think maybe you can look at your mobile itself. 1 year back or 5 years back, what your mobile was and what your mobile now. Similarly, the servers also 1 year back, what it was and now it is. If you see the power demand, they're becoming more power hungry. Each server is becoming more power hungry. That means the rack space available, you need to continuously expand, or you have to increase your power density that you can transfer from your source to the servers. So there is increased demand in the power density, and also we need to work towards the power space saving in the distribution. And also there are innovations happening in the modularity and the speed of installation, because the way in which the data centers are growing, earlier it used to take around 3 to 4 years or 5 to 6 years sometimes to construct a data center. But now the demand, the expectation from the field is that they have to be more modular, such that they can install the data center within 6 months. And that means we need to make our products more modular, more scalable, and we have to make it more safe and reliable. And also we have to ensure that serviceable and maintainable. And on the digital front, it's not just making the product available, but we need to ensure that we need to continuously monitor. Like say, we need to ensure where the losses are happening, how to make it available. And also, like say, we can go to the next levels where, suppose if we have a green mix from the incoming data, so we should be able to convey to the servers that, okay, now you are working on a green, so you can use more energy, but when you are working as a fossil fuels, you can use less energy. So these kind of instructions we pass through these digital management techniques, such that when the servers are processing non-critical data, they can decide which power, which kind of power is available. Based on that, they can decide. And also we have to make our devices also cyber, I think, secure. That means it's not like in the today's world of the security threats or the connected devices, there are cyber security areas or concerns are there. So we need to make our devices secure. And there are new technologies, I think, within the data center power, like now the distribution is AC, but there could be situations because each server now accepts AC power, but there are changes where to transform the AC data center distribution into a DC. And also there are new trends evolving in the storage technologies, but still I feel we have not reached a break point in the storage technologies, and still we need to do the innovation in that areas. And also in the data center, there are debates and discussions or innovations going on in the areas micro versus mega, whether you want micro data centers, like small data centers at multiple places, or you want to go for mega structures. And another area is like green mix. So that because as I mentioned, the 20% of the total power consumption on Earth is going to be used by data centers. So we need to ensure that these are environmentally they are friendly. So that means they need to consume more green energy and less fossil fuel energies or less polluting energies. And also we need to comply on the regulatory, and we need to optimize the energy cost. So in the view of the increased data center power consumptions. Okay, these are the areas that I think that power electronics is evolving in the data center areas. But yeah, so when you want as an individual, I think you might be looking, okay, what I will do if I come to in these areas. So there are three, I think I just listed 3 areas. It could be, I think there could be multiple areas. Like say you can work on the core power electronics, wherein you will be either you're on a research side or you're working on the electrical or the core power electronic concepts. It could be switching devices, or it could be power conversion, or it could be power conditioning or cold storage. So all these areas, that means you are working on the core technology on the power electronics. But you also will, I think we can also work on as a product development areas, where we will be providing solutions, like that means how to design a new data center or power distribution, or you can work on the system engineering, how to develop new products. You can be a thermal expert based on your understanding of the losses where these in the power conversion is happening. You can also become a hardware engineer, where you will be designing the boards, or you will be designing the sensors and signal processing. And you can also become a firmware engineer, where you'll be working on the converter controls by using other FPGA, microcontrollers, DSPs. So all these areas you'll be working on towards the product development. But apart from this, you also can work on to the data sciences, where you'll be working with your power electronics knowledge to look into the areas where we can collect the data and we can make these power consumptions more efficient. So you can use our techniques like in the areas of innovation, in the, let's say, machine learning. You can incorporate all these techniques or the data that we collect. We can make models, and we can design products, and we can make the products behave such that they face all the consequences of, let's say, how to make it more efficient or more, what you can say, more manageable. So with this, I just wanted to conclude. Maybe this is a small cartoon. Maybe you can just check yourself. I think the data centers are becoming huge, and they're becoming power hungry, and they need critical power. That's where we need to continuously provide technologies in this area. Thank you, Kaushik, and this is from my side.
Thank you, Mr. Bhaskar, for this interesting talk on power electronics for data centers. So I will again get back to you with few questions and we'll discuss. So now I would like to invite Mr. Ratnakumar Devraj, Industrial and Systems Development Engineer, C&T Power, Belgium. So Ratna Kumar is Industrial System Development Engineer at C&T Belgium. He holds a 15 plus years of experience in R&D, engineering, project management, expertise in new product development, low and high power inverter systems, and industrial control products. He managed different teams inside group, company, developed products in compliance with established phase gate process. He has multidisciplinary working across department, collaborating with teams and knowledge benefits. He has hands-on working beyond the design of the product and to handle large action scope, kickoff design, prototype, validation, installation, and commissioning of products. He is a strong individual with his commitment to business development, excellent communication, organization, execution, and leadership skills, focused on 100% customer satisfaction, and handled customers, partners all around the globe. Ratnakumar received his BE degree in Electrical and Electronics Engineering from University of Madras in 2002 and ME degree in Power Electronics and Drives from GCT Coimbatore under University at 2005. He is a senior member of IEEE Madras section, and he lives by the golden rule: start with nothing, finish with victory. He has inspired to create, innovate products and technologies that can have a true impact on global market, meeting international safety compliances and standards. So Mr. Ratnakumar will be talking about power electronics for telecom applications. Welcome, Mr. Ratnakumar.
Yeah, thank you, Kaushik, and thank you for my co-participants and students of Amrita Institute of Technology. Could you able to see my slides?
Yes,
Could you able to see my screen? Yeah.
yes. You have about 15 minutes. Okay.
I'll try to see to finish as quick as possible. Thank you,
Thanks.
Kaushik. Yeah.
Thank you. Thank you. Yeah.
So I just try to introduce about my company, C plus T Power. So what we do is we design, manufacture, and market a range of power backup products for industrial operators and with for the mission critical applications. So when it comes to innovation, that this is one of the example where we can show that we are the winner of the Little Box Challenge. It is the contest to develop the smallest inverter, which is done by Google and IEEE, and we have won this contest, which is $1 million. So this is one of our boost for the product we develop, and we are worldwide here. Just to show that I am located in Belgium, that is a headquarters where I am located, and we have several other production and R&D facilities around the globe. So I just go into detail for the presentation. So the telecom network infrastructure, what we see today's infrastructure, we see that the mobile networks today, so we evolved from 2G and then we go to 3G, 4G, and now we are looking out with the 5G. So where we at the 5G level, we will go with the small cells. We have a BTS, and then we have the basic switching center and the MSCs. And we are going to see how the power electronics products are being going to be evolved in the next coming future for the 5G. So you see the graph for the mobile internet evolution. So we can see from the years how it has been evolved. And you see the mobile internet users have been increased day by year. And then there is a lot of traffic due to this. And how does the telecom involves? You see the small BTS cells and the small cells where now people are more involved in looking for more data, where the revenue is increasing, and the subscribers for the mobile, they have increased to now for like 5.7 billion subscribers. And then there is a development for telecom for sharing the business. And there is also with the 5G, you have to see that the radiation restrictions are being taken into care. And because of this, now the telecom market is increasing a major shift from different from 4G to 5G. And so now we see that the evolution. So it took almost like years to come up with the 5G broadband. It took almost like 20 years to come to that level of extension. But still, there are some countries where they are still don't have the telecom facilities. So the people are going to still use the 3G and 4G, and they have some investment on the deployment for the telecom. So what is the AC and the DC power inside the telecom centers? So when you see the telecom center, this is just a basic building block. So you have the power utility, you have the standby generator and ATS. And what is the major telecom DC power is the rectifiers here. When you think about the power electronics, you have the rectifiers which converts AC to DC, and then you have a big battery bank to store the DC, which is 48 volt, and then you have the telecom loads, which is nothing but they are operating from minus 48 volt DC. So all the telecom like transmission or radio equipments work from the DC voltage. And if you see the AC part of this telecom, where they have those inverter, the UPS, which is located here, so they need an additional battery banks here, and they have the AC loads. There is an IT or the telecom data centers also available where they need the AC load is supplied to the server racks through the AC UPS. So this is the typical the layout of the AC and the DC power on a telecom. So what we can do with the product is we can have the rectifiers, we go to the batteries, and we can have a system with a modular or a standalone or scalable system for the application. So this is just a typical example of a cabinet where we can have the rectifier part, and as C plus T, we are giving our inverters here to give a complete solution for AC backup. So what is the market expectation for the telecom centers? So the expectations is to have a more available and reliable product, and it should be more simple, flexible, adaptable, and scalable. And they also have to reduce their operational expenses, because the product itself should have high efficiency and should have a better carbon footprint, and to also save the maintenance costs on the repair of the electronics, which means that they should have a high MTBF in this case, and also to have the battery life expectancies, and there should not be any more oversizing and they provide a pure energy to the loads, which means that they reject the typical grid disturbances what they have. So as I said that you have the three major point here to discuss is the reliability, the availability, and the serviceability. So as I said, how to increase the availability is to add the redundancy concept over here and minimize the chance of the human error, select the high quality and reliable equipment, minimize the downtime, and standardize the service concept. So how C++ provides solution to the telecom segment? So we have a company which is started in 1936, and then there is a group of evolution where we come up with our new concept with the modular systems. So in 1996, we propose a high availability with a smart AC solution fulfilling the TRS criteria, which is nothing but true redundant system criteria. So based on this, we have several evolution of modules before, and we are the first company in the world who have introduced an hot swappable AC backup inverter solution, which is modular. We call it as the TSI, which is called twin sign inverter. So this is a module which is like 2.5 kVA and 2 kilowatt. So it's a modular inverter. It's not an UPS. And this concept will allow to eradicate the single point of failure when compared to the traditional systems which we are going to see later. So what is our main idea is the goal is to secure the loads, the DC loads and the AC loads. So as I said in the telecom, so you have the grid and you have the conversion AC to DC, the rectifiers, and you charge the batteries, and you have the DC load. And when you come to the AC load, what is the solution? What is the conventional solution they had? So they have to use an inverter here, which takes the DC from here, from DC to AC conversion, and there is a static switch available, which is now then feeding to the AC load. So what is the disadvantage of this? So if you see there is a single point of failure with the help of the static switch, you see when static switch is failed, then you lose the load. The AC load is more critical in this case, and you have the AC loads were nothing but the value added service servers, which are kind of in the data centers, in the telecom data centers. So what is our solution where we provided is with the TSI modules, or the technology what we introduced is to feed the AC to AC conversion here, and then we take the DC from the existing battery, and then we can make a conversion from the DC to AC to supply the AC load. So here we try to avoid the single point of failure. So as I said, so when AC is present, you directly take from the grid and you make a conversion from AC to AC, and each module inside the TSI has the static switch implemented. So it is hot swappable, it's hot redundant, so you can easily unplug the module and you can plug a new module in case of any failure. And the second point, as I said, since we use the existing DC here, so you can take when AC is not present, you take the DC and then you make a conversion from DC to AC, and you can still supply the AC load. So when compared to the UPS and how we different from the UPS and our inverter product, so you can see that for a traditional system, you have the rectifier, the batteries and the charging, and then you have to use an UPS in this case. So you have to provide separate batteries for these UPS segments. You are oversizing to bring the redundancy. So the AC branch is not expandable. So you need a critical maintenance contract for the UPS in this case. And how we are differentiating the UPS concept with our inverter system is that, so you have using the same batteries which are in the telecom to power our inverter. So there is only one single battery for all types of applications. So there is no oversizing. So we can go with any type of configuration here. There is no maintenance cost. It's hot swappable modules and no restriction in the autonomy here. So as I said that the telecom operators need more availability in this case, no single point of failure, good noise rejection. There should not be any transfer time when conversion from AC is not present. Then you need a high reliable product, which is the mean time between failure should be high. In terms of maintainability, it should be a modular, it should be hot swappable, and the modules are lightweight that even a normal person can do the manipulation. When compared to the operationality, it should support for expandability, any load variations or inrush currents. Even compared to the cost, it should be highly efficiency. The product should be highly efficient. It should have low harmonics and high power factor. When it comes to the infrastructure cost, it should have a less footprint. and then it should produce a less heat. In this case, the losses should be less. So all these operators needs are being taken care by C plus T with our TSI inverter solution. So our solutions for today's segment, so I have a different range of products we have been working on. So we have a standalone modular inverters, UPS for data centers, and also for we are working with the multi-directional converters. So what is the value proposition we give to the customer? So it's highly efficient. Our inverters are efficient. AC to AC conversion, the efficiency is 96%, and from DC to AC, the efficiency is 94.6%. And also high availability, because high availability is very important in case of the data centers in telecom. So we reach almost six nines on the availability and more. As the scalability, when you see that we can go from small power to large in megawatt power also is possible, is scalable, and it's also easy handling, where we can introduce a hot swapping feature, and it has a low mean time to repair. So when you see that the impact is to have a less operational expenditure in this case when compared to the competitive our competitors. So we have different kind of power converters which are applicable to the different segments we are going to see later. So it's a different name, and we have a different power level. It can with 230, and it's working from the DC in. So we have a 230 or 120 odd for the US market, and we also have big inverter range in this case. So you can see the efficiency here. So all the efficiencies are given here for this range, and also the modularity, we can increase the power to different level. So this is coming with the another technology called the ECI, which is Enhanced Conversion Innovation. So this is a new product which is having more increased efficiency when compared to the other TSI inverter. So where I see that I told you that the inverter efficiency is more in this case with this new technology, or a new converter which has been used inside the modules. So what the customer needs is a peace of mind. He needs an outstanding user experience. You should have a trouble-free, lower expenses, and more data, not more power. So I just show you how the telecom data center architecture looks like. They go with N plus N redundancy. So from the source to the load, they go with a complete redundancy. You see, you have a transformer for each feeder A, B branch, and then you have the genset separately. And then if you see that you have the modular inverters, which are located there completely, and then you go to the loads over here. So this is just an architecture to show about the telecom data center, and this is one of the layout I shown with the A plus B system. So you have one system which is called as A and the B, and then it's completely the modules are modular, it's hot swappable, and so on. All the features are being incorporated here. So I just took one of the example where I worked 8 years before on a project for Vodafone India. So this is one of the picture which is shown here. So this is the model which was being developed in the factory, and then later it has been installed with one of our partner. So this is the installation picture where you can see that all the modules. This is system A and the system B, and then you have a synchronization unit which is here. So you can see that it's installed on the third floor with a raised floor. You can see. So they have just installed the complete cabinet over here. So coming to the market, so our products are used in variety of our applications. So I just took one of the application is the telecom. So as we know that the 5G is coming up, so you can see that we use our standalone inverters, or we promote the standalone inverters for the telecom for radio equipment, so like the 5G antennas or the Wi-Fi repeaters, and also for the BTS and the MSC units where we need a maintenance equipment. What are the type of loads we have is the maintenance equipment such as computers, IT servers, and so on, cooling equipments and security systems. So this is the telecom infrastructure which has been changed or evolved due to the 5G. So you have small cells now to have a small users to increase the bandwidth. If you have a lot of users on the same tower or the cell sites, then you decrease your the availability of the data. So they are trying to split into small cells that with 5G, and then you go to the exchange or the server units, and then you have the main exchange units. This is just to show the telecom architecture here. And as I said, so you will have a very smaller units which are even trying to be located on the pole, so that the user can experience or they can have the higher bandwidth for everybody. So you have the main station, base station, and then you have small cells which are located everywhere in the like 50, 60 feet. So this is just to give the example of how the small cells will be, a cell type can be installed. So you can see that within 50, 60 feet, you can have those small cells where you can have like 4 to 6 persons users who can operate. Or if you have a bigger distance like 1 meter or 1 mile, then you have a lot of users there. So this is trying to get reduced and to have the users to experience more data in this case. So I'm working on one of the project which is for a 5G. So we are working on one of the project called MetroGrid. So this is a microgrid solution based on the DC distribution, where here we provide our solution here. So we have our inverter modules here, which is converted to AC to DC, which is 48, and then this 48 we have a DC-DC conversion, 48 to 380 volt, and we are trying to use the 380 volt DC bus for the transmission and also for all the small cell sites. So where again you are going to make a conversion here. So they use the high voltage DC for the long distance transmission. Yeah, this is one of the project. We are working with a customer in US actually. And you know that most of the companies, they are trying to work on a different deployment for the telecom especially, and we are one of them who are working on this segment. So, and we also have other possibilities to use.
Sorry,
Yeah.
Sorry to interrupt. Can you wrap up in a few minutes?
Yeah, I'm just finished.
Can you wrap up? Yeah, yes.
I'm just finished. Just 2 more slides.
Yeah,
so we are
sure.
going with telecom edge computing, where we can go with the AC and the DC loads. So we have a different solution in this case where we use a multi-directional converters. So when it comes to applications, so as I said, we have the cell sites, we have the regional nodes and the central node, the MSCs. So here we have different products. We are trying to provide a solution for the customers, so where we can have the different inverters to at different levels of the telecom networks. So these are some of our references, and the future of the conversion is now we have already deployed this. So we are now coming with the ECI, which is the bidirectional converters, where we can have a bidirectional at all the ports, the DC ports, the AC in port, and the AC output. There are several other possibilities. We are trying to work out with different customers on this. Thank you for your attention. I hope I could able to cover up my presentation. Thank you so much, Amrita and Kaushik. Back to you.
Hi, Ratnakumar. Thank you very much for your nice presentation. And now what we are going to do is we will take 5 minutes for each speaker, and I'm going to summarize what has been said, and then maybe I'll ask a question, and I'll take a question from the viewers. Okay, and then we will finally summarize, and we will finish. Okay. So just give me 1 second. So I will come back to Dr. Swaminathan. So Dr. Swaminathan actually he told us that how the development of sustainable, clean, and reliable energy infrastructure is going to be so important, and then and that is opening up a lot of opportunity and a bright future for people of all of us who are working in this power energy sector. And so I will ask a quick question. Dr. Swaminathan, are you here? Okay. Hello?
Yeah. Yes, doctor.
Yeah. Just one very quick question, because we have a lot of students listening today. So if you can tell us a little bit about what are the essential skills that you are looking for an engineer that you would like to hire for your challenging products. I mean, what they should know.
Yeah, it's an interesting question. See, when it comes to hiring, what we look for from the students. So normally, so the students, when they come for an interview, so they claim a lot of things that I know this, I know that, blah, 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 blah. But what we precisely look for is the right attitude, work attitude. so you should be up for any challenge, and you should have the you should be passionate about what you are doing, and you should be inclined to the work culture or work environment. So that is the primary requirement. The second thing is, so you should have a strong fundamentals or basics, because we don't expect the the fresher or the GETs to design an inverter or converter whatsoever from day one. So you will be given sufficient training, and you will be mentored by the senior people. But what we look for is you should have a basics, because we what we look for is are you a right guy to invest? Because as an organization will invest a lot of things on every employee. So is that so? Like my investment is going to give benefit or fruit someday, say in 1 year or 2 years. So for that, you should have the right attitude and right mindset, that we should feel that you are fitting into the organization's culture and environment. And also you have the basics, like the strong fundamentals. So we don't expect anyone to start up like a NPC topology converter,
Yes.
high-level converter
Yes.
on day one.
Correct.
Yeah.
Great, great. One more very quick question for you is that at Schneider, Bangalore, right? So
Yeah.
what is the most next challenging converter project that you have?
Yeah, presently
Just
we are working
briefly.
on developing a grid tie inverter for 50 kilowatt, 55 kilowatt and 50 kilowatt grid tie inverter. So again, so every country has got their own grid code. So we need to
Correct.
play with all the grid code, and so like a lot of new development happening on the grid code side. We need to comply with the latest standard and qualify our product in each and every country on the planet. So that is the
Right.
challenge we are facing. Also, we started working on the hybrid converter, like kind of a microgrid concept. Microgrid, I wouldn't
Right.
say microgrid, it's a nanogrid we are working on.
Okay. Okay. Great. Awesome. Awesome. Thank you very much.
Thank you.
So thank you. So now I will quickly summarize what Vishal told us about fuel cells. So he talked about grid integration of megawatt level fuel cell, and then he summarized the challenges that one face while developing grid tied inverters, like anti-islanding and meeting with all the grid codes. So one quick question for you, Vishal, is that from your experience, what is the most most difficult thing that you faced while meeting the grid codes? So what is the most difficult specification that challenged you?
So we had developed this inverters ground up. So one of the because when we started doing this, none of us had worked on all these anti-aligning algorithms. So getting the converter passed through anti-aligning was one of the most difficult, challenging things that we had done, because the testing itself involves it takes about 1.5 to 2 months of testing. Earlier, the first time when we did it, took up almost 2 months of testing, and we had to tune the island and repeat that successfully, tripping each and every time. And the certifying agency, that is UL, when we are working with US, so the inspector will come and check whether it is correctly tripping for all the different conditions. And we also had difficulties in getting it passed through UL for the safety standards. This is for the grid side, and also since we are doing industrial control, we had to ensure that our software is also passing through the software standards. That is the UL 1998 or 6730. Those are all standards that we have to comply our product with.
Right.
And since we are doing it the first time, we had a lot of difficulties there, but somehow he did it and also learned many things.
So I have a very quick question, and I want a sort of a small answer, but direct answer for you. So, what will be your suggestion for people, for students who would like to enter this area?
So suggestion is it's a very exciting area, and but unlike software or services where there is a lot of hiring opportunities, you would find that there are not so many opportunities, like only a handful of companies. So in terms of employment generation, I would say very realistically that we cannot afford or give the numbers that software gives. But the people who do join, they get really lot of challenging opportunities and a lot of areas to work. So let's be practical here. We cannot match the Infosys and TCS, and we don't have that much requirement.
But of course, the thing is that where you are also looking for a workforce who are trained in hardware, the opportunity is
Definitely.
also
Opportunities are
small.
there and a lot of challenges. But
Right.
if they come in with the wrong or not wrong, incorrect priorities, thinking that we can match the numbers like what TCS or Infosys or the software services
Right.
segment gives,
Right.
that is
Right.
not going to happen. We have to be clear
Right.
about that so that students know for sure that the number of
Right.
companies and challenges will be limited only.
Right.
But once you are showing that you are there among the best and you have the talent and you have the fundamentals right, then you will definitely get hired.
Correct. Right.
And like
I
what
think
one of the other panel members
Swaminathan
taught, I
also
think
said.
Bhaskar has told,
Right. Right.
not only about the development of hardware, right? There are other areas within hardware also, like in terms of firmware or in terms of data analytics for this kind of application is also there. So we cannot
Correct.
discount that. So we need to
Correct.
diversify in terms of that
Correct.
in the skill map.
Correct.
Yeah.
Correct. Correct. Thank you very much, Vishal.
Thanks.
So now, Mr. Sarvanan from Alstom gave very interesting talk on the power electronics in traction, and he's the moving power station is an amazing concept, and it's great that actually they have been able to make it happen, right? So. So he summarized. So you summarized the power electronics architecture with PEBBs and how the industry is slowly moving from IGBT to silicon carbide, right? So there are a lot of interesting challenges for hardware and software engineers, right? Communication guys and everybody, right? So I have a very quick question for you. Is that you mentioned about this medium frequency transformers, right? Which is the upcoming new technology. So can you briefly tell us an example project where this has been implemented?
Okay, it is an example project is done by if you okay, I have some bonus slides because or else I will not take much time on it. So it is done by Alstom and it is done by Siemens and it's done by ABB and it is done for the mostly on the shunting locomotives. You know what I mean? It's not directly deployed on the passenger locomotive because of the reliability stuffs and things, and it is done on the shunting locomotives with the 6.5 kV device, approximately 750 ampere system, and the DC link of medium frequency is approximately be challenged between 500 hertz to 1 kilohertz. So that is the medium frequency, and the low voltage DC link we created is approximately 1800 volt DC link. So the 1800 volt is going to drive the inverter of approximately the motor power is equal to 275 to 300 kilowatt, and it is 4 motors in parallel, so that is approximately 1.2 megawatt is the total power of the power of the train. So it is done on mostly on the shunting locomotives. ABB also done the same concept. Siemens also done the same concept, and the power level is limited to 1.2 MVA. So this done, but it is not fully deployed on the high speed or in the passenger application due to the reliability stuffs and the reliability study is now it is getting progressed. So it is the only point behind it why it is not fully developed, and the advantage of gate drivers, enhanced power electronic building block, it's still under development in all our domain of medium frequency applications. But it is going to play the role. It is going to play the role, and rule the traction as well. When your SIC comes into picture, we are planning to go to 5 kilowatts also for when it comes to SIC applications.
Right. See,
So
just for the listeners, I will quickly tell you what is this problem that I think you, Mr. Saravanan, already told us. But see, this is a very interesting technology. So what is happening is that you have the source and the catenary, right, which is at I think 25 kilovolt, correct?
Yes.
25 kV around at that. But you need to drop that with drop the voltage, right? With a transformer. Now the size of the transformer is inversely proportional to the frequency. So
Exactly.
50 hertz transformer is very large, it is big, and you are putting this transformer on your moving locomotive. so it increases your dead weight, right?
Exactly.
So the thing is, but now using power electronics, you can change the frequency that this transformer is going to see. That I think Mr. Sarwan mentioned is about 1 kilohertz, from 50
Yes.
hertz to 1 kilohertz. So that means a dramatic reduction in the size of the transformer by 20-fold, right?
Yes.
So that is what it is. Thank you very much. Very
Thank you. Thank
interesting.
you.
Very interesting. Very
Thank
interesting.
you. Thank you, doctor. Thank you.
Okay. So now Mr. Bhaskar Reddy told us about the energy infrastructure in data centers. This is also very interesting, and I didn't know this very interesting statistics that today about 5% of the electric energy is goes into data centers, and it is going to become 20%. I mean, 1/5. So that's amazing. That's mind-boggling. And he also I think listed the challenges that and the opportunities. I think you have nicely listed the challenges and opportunities for people or the students or whoever looking for a job in this area, as in core power electronics, also in the product development, which involves embedded, then thermal design and all other auxiliary areas, and also data sciences. So I have a quick question for you, Mr. Reddy. This you said that because we all understand that it is very critical that we continue to power in the face of any fluctuation. So for that you will go for this modular architecture, right? So
Yes.
here we are talking about megawatt to 500 megawatts. So I would like to know that in this modular architecture, what is this module powers? At what power one designs these modules?
The module power is as low as 20 kilowatt. I think it depends on, like, say, what type of modularity we are talking about. I think when you're going for a like, say, vertical plus horizontal, so you'll have 20 kilowatt modules going into the UPS, and that will scale up to let's say I think different ranges up to 200 kilowatt, 400 kilowatt. But there are modules up to 200 kilowatt which can scale up when you are modularizing. Then it can go up to 4 megawatt.
Okay, very interesting. And then why one would like to go for this micro versus mega? Like mega is obviously like it is centralized, right? And you have to get all the connections there from the IT perspective, and also you have to get the power also in a localized place. So why not we go for this micro or nano data centers? So what is restricting us doing that?
Yeah, so one is actually, see, the data is typically you're storing in I think storing and processing. Generally, you don't need to be I think commercial spaces, like suppose in Bangalore if you want. So your data need not be here, so it can be somewhere else. So that makes you that, like, say, you can build a huge data center where, like, maybe where the land is not usable. Let's say in Rajasthan, maybe in Thar Desert, you can put up a data center and you can utilize that land, and you can build a huge data center. So that becomes a mega data center. And your data is out there. And you have, I think, your connectivity, your network connectivity speeds have improved a lot. So you can, I think you can. It's in gigabytes of data for on the Ethernet, and I think different communication methods. So, and with the fiber, I think all other technologies which are coming in. So there is no issue on the connectivity part. So you can get anything. So when you have a space, you can go for a mega. But there are some solutions when you want a fast turnaround of data. It's like, say, I want the data to be available very quickly. So then you have to look for micro data center. Suppose, let's say, you are building up a big mall, so where your data, I think huge data is getting generated. But for your data, you don't want to continuously send there to the mega. So you can have your own micro data center. You play with your data, but you synchronize your data with the mega data center. So that's where these two data centers keep playing. So I think right now, I think even if you see every one of us earlier, we used to store our own data at our home, but now I think most of us storing all our data into the cloud. And slowly even the computation also moving into the cloud. So that means you don't need to even have your own computational device. Suppose if you want to set up where you want four computational devices, it may not be on your machine. You can keep running them on the cloud, and you can provide services based on those computing devices. So both storage and computing is moved, but so it depends on how you want to access the data. Suppose let's say Netflix. So they might have huge mega data centers where they are storing the data, but for relaying, they might need a local. For caching, they may need a local data centers.
Okay. 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 Thank you very much. Thank you very much. Very interesting. So now Mr. Ratna Kumar from C&T, he told us about the exponential growth of the mobile internet and how the telecom market is evolving, and we are going from 2G to 5G. And he also told us about the basic architecture of a telecom data center and how does that look like with a rectifier, battery backup, and a 48-volt basic DC bus from where the telecoms units are supplied. So, and also he talked about a very interesting development of TSI inverter, which basically replaces the DC to AC part of the UPS, and also take out the reliability issue of the static transfer switch, right? So thank you for that nice presentation. So I have a very quick question for you. See Mr. Ratnakumar, you there?
Yeah, yes, sir.
Yeah, yes,
I'm
yes.
there.
So I have a very quick question for you. So the thing is that what I understand that in this, that from the DC link of the rectifier, right, of the UPS, typically
Yeah,
there is a DC to AC inverter, right, which is powering the AC load through the
yeah,
static transfer switch, and where
yeah,
your grid is also directly connected, right?
yeah,
So in case of a grid failure, that the DC to AC inverter of the UPS will take over, right, through
yeah,
the STS, correct?
yeah,
So, and you
yeah,
talked about the reliability issue with STS, and it may
yeah,
malfunction and things like that. But
yeah,
so the question is that for your TSI architecture, I don't know what is there in the box. Of course,
yeah,
that is proprietary, I guess. So my question is that you mentioned that still there is an inverter inside, and then you have a static transfer switch, and looks
yeah,
like you also have those three ports: one coming from your the rectifier DC link, another is your direct utility grid, and another is your load. So,
yeah,
so my question is that what is that innovation and what is different here that is making this
yeah.
more reliable, more efficient, and
Yeah, so you see that in the traditional cases we have the UPS. Okay,
right, right.
so the UPS, you have a less backup time. They have it on the telecom side, so normally it's like 10 or 15 minutes. So what
Mm-hmm.
we try to is to educate the industrial operators like the telecom operators. We had a quite a discussion to show how our product will replace this segment. Okay, so it's not
Okay.
quite easy because we had quite a lot of discussion debates with the experts on the telecom sectors. Okay, then
Right.
we try to explain them, no, you go with our inverter. So what is inside the box of TSI is that you have a
Mm-hmm.
AC conversion, so which is nothing but a double conversion which is taking place inside. Okay, so
Okay.
you have a
Okay.
DC buffer inside.
Mm-hmm.
Okay, in this case what we try to tell the telecom operators is that you use the DC which is existing in the telecom center, so there is no need of an external DC bank to be incorporated like in the case of UPS. Okay, so
Okay.
you take
Okay.
the DC from here, so our DC can be connected to the inverter there. So
Right.
whenever the grid is present, so you
Mm-hmm.
make a double conversion from there. So you utilize the AC input grid and you make a conversion to the AC output to the loads. And then
Mm-hmm.
when the AC is not present, you take it from the existing DC which is available in the telecom center. So I hope
Mm-hmm.
you got this point. So we
Correct.
try
Correct.
to
Correct.
utilize
Correct.
the existing DC from there. So there is no zero transfer time. There is no transfer time in this case. There is no chance of a single point of failure here because each module
Mm-hmm.
is a modular concept. So each modules are
Correct.
hot
Correct.
swappable and
Correct.
redundant. So in case
Correct.
of you a failure, you can easily swap it out and you can insert a new module there. So that's how we try to educate all the industrial operators or the industrialists who are in the panel on discussion, and they all accepted this, and that's how we try to implement a variety of telecom operators with this kind of TSI technology.
Okay, that's awesome. Okay,
Yeah,
okay.
I didn't go in
Thank.
detail with this because of the
No, no,
time.
of course
So
you have only 15 minutes, right? I
yeah,
think
so
we are
there is a
looking
lot
at
of
years of
things.
development,
Yeah,
right?
there is a lot of
Right.
interest that
Of course,
maybe on
of
our
course.
next session we can go in
Sure,
detail of
sure.
how these conversions are happening
Yes,
and how the new
yes,
technology.
yes,
Now with the
yes.
TSI, now we are coming with the ECI technology where you see you have the bidirectionality, and we are
Right.
exploring different applications here in this case. Yep.
Right, right. Awesome. So, thank you very much, Mr.
Thank
Ratnakumar.
you, Kaushik.
So, thank you. So, I have, so now I would actually like to get some questions from the listeners, but I don't see any question in the chat window. So, maybe we can take a very quick few questions. Deepa madam, are you there? I mean, are we going to take questions from the
Yes, sir.
listeners or?
Sir,
Yes, sir. There are, Shailaja ma'am will take it up. Yeah.
good
Okay.
afternoon, sir. There are some few questions from participants. Mr. Gangadhar Aki is asking that what are the power electronic devices used in locomotives? And from the same participant, there is another question. What is the power electronic technology in case of Hyperloop train?
Okay. Okay, the question goes to Saravanan then. It's
Yeah,
me.
of course, of course, of
Okay.
course.
Okay,
Yeah.
so the first question is nothing but the locomotives. I can tell you the devices are being manufactured by ABB, Mitsubishi, Hitachi, and Infineon. So we take all the devices, and at present in locomotive it is 4.5 kV device, 1200 ampere current we use in locomotives, and we use in high speed trains is a 6.5 kV device and 750 volt ampere devices. And in Alstom we developed now 12,000 HP locomotive. It is running on the field now. In last 3 months it is running on the field, where we use 3300 volt device and 1500 ampere, all from Mitsubishi. Mostly in Alstom we try to use Mitsubishi. Second is Infineon, ABB, and Fuji is mostly used for means most on the auxiliary converters. For the propulsion we target three main suppliers, that is from Infineon, ABB, and Mitsubishi. Coming back to the question of Hyperloop is more related to something kind of physics-based system. It's not like explicitly on the power electronics because I'm not working on to the topic. But I can throw some light on the maglev. Maglev is the same thing. It is called as a linear induction machine. So where the train cost is lesser than the track cost, the track costs more. Where the power electronic comes, and where the excitation of the magnets is done by the power electronic systems, and where the hyperloop and magnetic levitation is nothing but you levitate the train. In hyperloop you create the vacuum and we start running on the system. It's more like to physics. To be frank, I need to have I can reply back to your questions in the later stage because I was not fully deployed on the hyperloop. For the locomotives and our high speed trains, we more work on 6.5 kV, 3.3 to 6.5 kV. That is the
Sure,
voltage
sure,
range. Yeah.
sure. Thank you, Sarvanan. Thank you.
Thank you.
Madam, any more questions?
Sir, one more question. What is the power generation efficiency for solar panels at present?
Okay, I can take this question.
Yeah, sure. Go ahead.
So solar inverter, if it comes to inverter, we are targeting efficiency of 99%, even 99 point. It's going in that range. Like that is the conversion efficiency from DC to AC. Whereas for panel, it's way less. It's I'm not sure about the panel. Approximately, I would say like a 70 to 80% is the panel efficiency, but inverter efficiency is way ahead. Like peak efficiency is 99.45 in that range, and the CEC weighted average efficiency is 98.7, 98.8. So we are calculating in decimal point. So you can imagine how much sensitive it is.
Right.
But just to add to that, I think one needs to also look at the power level of the converter. I think what Dr. Ganeshan is talking about will be more in the central inverters, upwards of maybe 30 kilowatts. And when it comes down, maybe more string and the modular inverters, it will be around 96, 97. Just to add to what he told.
Right. See, if you add the DC-DC along with that, see the only inverter efficiency if you take, it will be in that order, like what Dr. Somanathan said. Like it will be 90 upwards of 98%, right, over the spectrum of power. But if you add the DC-DC, if it is not like a central inverter where you have the low voltage panels you are taking, particularly for single phase systems, there the efficiency will hover around 94, 95, 96%. But the thing is that there are other stuff, like if you take the transformer, right, the transformer efficiency is also adds about a percent, which is typically connected in a central inverter system. But that is the picture. We are doing quite well, but I think on the solar panel it is quite low if you look at the incident solar energy to the actual electrical power generation, which is quite low. Okay, thank you very much. Thank you very much.
Sir,
Okay.
can I ask
Yeah.
one? Yeah. Hello, sir.
Yeah, madam, please go ahead. Please
Yeah,
go
yeah.
ahead. Please go ahead.
One participant is asking, electrical graduate who is looking to pursue masters, which should be his choice apart from his interest, so that he can be more advanced in career and safer side.
Okay, so anyone wants to comment on this? So I don't know what does this mean, being safer side.
I think today in today's scenario, nobody is on the safe side. Everybody is on the vulnerable side only.
Exactly.
Yeah, but having said that, there is no silver bullet. Means there is no one-stop solution. So today's expectation from the industry is the candidate must be he like what one of the panelists said also. When we look for candidates, what we are looking for is not really a person who can solve solutions for the company, but rather a person who is rooted in fundamentals. So when we interview candidates, we don't ask him even what he did in masters or his project. What we look for is fundamentals. So if the fundamental grounding is very good, we ask basic questions only. We ask only high school math and first and second year of engineering. That's all we look for in a candidate. Only if he's very grounded in those fundamentals, then any training or anything that the job requires will be done as a part of on the job training, or what happens in when he joins the company. We don't expect on the first day the candidate to be able to solve all our problems, but he should be adaptable to change and be able to take on challenges. For that, the grounding is all the fundamentals. So the
Just
candidate
to
should not.
add on to that,
Yeah.
sorry,
Please go
just
ahead.
to add on to that and to support your statement, I've seen lots of engineers who have gone into sales and also succeeded in that. That doesn't mean that you have to take MTech itself. It's your sole kind of like passion that actually leads to it. If you are actually determining regarding salary, so there are lots of people who have high salary and are still not satisfied with their jobs also. So that could be a criterion that needs to be addressed to by the candidate. It's not an answer that can be given by anyone outside.
Right.
Right. Yeah.
Exactly. So
Okay.
just to add one more small point, just we can just compare with you the title and the brand value. So, for example, you had an ME in power electronics. It's giving you the title, and how you maintain the brand value is nothing but you deploy yourself on that field, so that you will come to know. For example, you have a doctor who is a pulmonologist or a cardiologist. He has done his masters in that domain, and he take that same domain till he retires. So that is called as the brand value. The brand value makes you more safe to answer this question. For example, if you are in very that power electronics, you do the PhD, you do the PDF, you stay in power electronics, the system will drive you, and you will have more, you will feel more safe as and when you gain your experience. So my point is that you have your title, stick on to your brand value. So if you're ME Power Electronics, stick on to that field. Okay, the field is very, as you told, it's very not like as Vishal suggested. It is not like a hype like what software companies provide. So if you have that brand value, it takes you to the safer zone of operating area, like RBSOA, reverse bias safe operating area. You will be in that the same domain. So it seems like that.
Yeah.
Yeah. Thank you.
Yeah. Right. Thank you very
Thank
much.
you.
Thank you very much. Any
Thank you,
other
sir.
questions, madam? Maybe
Sir,
our
yes,
last
sir.
one
Yes,
question
sir.
we'll take.
Yes,
Just
yes.
one
What is
question,
the
last question.
yeah?
Yeah.
What is the
Okay.
focus of power electronics in electric vehicles?
Okay. So anyone wants to answer? Okay, I can pitch in. So see, in electric vehicles, so the main traction generator is, instead of a diesel or a petrol engine, here it is an electric motor, right? So now to power the electric motor from the supply, right, you need a converter that we are always talking about. See, the motor is a AC motor, most likely, right? It's an induction motor. So in order to run that induction motor, you have to I think it is echoing. You have to run it from an energy source. Now your fuel, the energy source in a car is your battery, which is at DC, right? So you need a power electronic converter to convert the DC to the AC to feed to the motor. So that is where the power electronics come in, right? And also the battery, your fuel tank, right here, that battery also needs to be charged. Now this battery is a DC, correct? Now you have to basically plug into your utility or the supply, which is our AC, say 230 volt or 400 volt 50 hertz AC. So then again you need a converter to convert that from AC to the battery voltage, which is DC. So basically there are two things. One is your drive inverter, which is taking your battery energy to your motor, right, to drive your car. And again another converter, which is your charger, which is converting from AC to DC, right, where you're charging your battery, and that is what we call charger. So these are the two important units in the electric car where you will find power electronic converters. Okay. And now the thing is that the field is evolving, and I mean we can talk about it for hours of current challenges and what is going on. But just to summarize, the charger and the drive inverter, these are the two places where you will find power electronic converters inside an electric vehicle. Okay. All right. So, madam, any more questions? Otherwise, I think I will just
Yes,
thank
sir.
everybody.
Yes.
And
Yes, sir. Thank you.
okay. Okay. So I would like to thank for Amrita to organize, and particularly Deepa madam and her colleagues to organize this very interesting and relevant panel discussion on applications of power electronics in various different areas, starting from renewables to electric traction, data centers, and we had an excellent panel discussion, and our speakers gave up to date current technology, like what is going on and where are the challenges and where you can actually jump in. And I believe what Dr. Swaminathan said, that actually, given the growing power demand, and given the every day the new challenges that it is bringing, I think that we have a bright future. Like, see, if I ask that, if I answer that question, that whether you have you are you safe in this area, see, you are safe in an area only when there are problems still open in that area. And then only there is a demand for you. Then only there is a need for innovation, and you have work to do. So otherwise everything is automatic, right? So the thing is that, given that perspective, I think that if you choose a career in power electronics and allied areas, I think you are going to have an exciting future in this area. I think that is what comes out from this discussion. And I would like to sincerely thank all our speakers, Dr. Swaminathan from Schneider, then Mr. Vishal from Bloom Energy, and Mr. Sarvanan from Alstom, and Mr. Bhaskar Reddy from sorry, for giving the talk from ABB, and Mr. Ratnakumar from CNT. Thank you very much for your exciting talk and your answering the questions and throwing light on what is going on. And thank you very much for your time too. Okay, so I think from here I want to hand it over to the organizers. Okay.
Thank you, sir. Thank you, Kaushik, sir. Uh, I take this opportunity to thank our director, Brahmachari Dhanraj Swamiji, our principal in charge, Dr. Nagaraja sir, our chairman of Triple Department, Dr. Rashmi ma'am, and vice chair, Dr. Mini Sujit ma'am, for giving us constant support for organizing this wonderful webinar or panel discussion. My special thanks would be for Dr. Hariram sir, who has conceived this concept and without whose help this would have not been possible. This 2-hour session was a miracle. This would have not been possible without our speakers and our moderator. It's my privilege to having been attending the session, and I'm sure that the students also would have benefited the most. Sir, Kaushik sir, this was excellently organized panel discussion. The way it was organized, technically sound concepts and all those things, it was really very, very good. Thanks a lot from Amrita side, sir. And I thank the speakers for having accepted our invite in a very short notice and sharing your technical expertise to our students or the budding engineers who would definitely be a part of power electronics in near future. I would also like to place my sincere thanks to the MTech admission team of Amrita, Ms. Sujitra and Nalini for their constant support. I would fail in my duty if I would not thank my co-host Shailja madam. Thanks a lot, madam. And without our students' help, this would have not been possible. Thank you, Jagdish. Thank you, Revant. Thank you, Pavan. Thanks. At last but not the least, I would like to thank all the participants for your patience. This would have not been possible without your support. Thank you all. I would sincerely like to thank all the speakers and the moderator for giving us a wonderful session and making our day. Thank you. Thank you, sir.
Thank you, ma'am.
Thank you.
Thank you very
Thank you,
much.
Deepa
Thank you
ma'am,
very
for
much.
Thank you. Thank you very much. Thank
Yeah.
you.
Thank you.
Bye bye.
Thank you,
Bye,
Deepa
ma'am.
ma'am, for
All the best.
organizing.
All the best to
Thank
all.
Okay.
you, Kaushik sir, for moderating, and I also my sincere thanks to all the panel members. Thank you so
Thank
much,
you.
sir.
Thank you, ma'am.
Thank you, everyone. All the best.
All the
Thank
best.
you. Bye-bye.
Thank you, sir. Participants, we are dismissing the meeting. Thank you all.
Thank you, ma'am.
Thank you, sir.
Ma'am, let me
Sir.
know. Ma'am,
Yes, sir.
hello.
Hello. Yeah.
Ma'am, when will be the next webinar will be held, and where can I get the information about it?
We will give you in your mail IDs. We have your mail ID, so we will definitely send all the information in the mail IDs.
Okay, ma'am. Next time we will come up with some other topics or.
Yeah. It would be a different topic in the area of power electronics or in an embedded system for sure.
Okay, ma'am. Thank you very much, ma'am.
Yeah. Thank you. Thank you.
Ma'am, certificate. What about certificates, ma'am?
We will send you in 10 working days because students are also busy with their examination. Please kindly wait for 10 working days. You will definitely get in your mail.
Okay, ma'am. We need to fill any forms for that or?
The feedback form, whatever you filled, would be more than sufficient.
Okay, ma'am. Ma'am, feedback form link, ma'am.
That was already there in the chat window. Can you just browse your chat window for that?
Ma'am, how to go for chat window, ma'am?
On the bottom, you have your mute and video symbol, right? Next to that, you have a chat and participants list, a chat window, like messaging window. Right? If you just click onto it.
Ma'am, I don't have that, ma'am. One speaker icon, one video icon, one speaker
video icon. Yeah. Next to that, you have a hand symbol. Do you have a hand symbol?
No, ma'am. No, ma'am.
Okay, then just let me know your name so that I'll send it to your mail ID.
Manoj Kumar, ma'am.
Manoj Kumar. Yeah, Manoj. It will be sent to your mail ID, Manoj.
Okay, ma'am. Thank you, ma'am.
Thank you, Manoj.
Thank you, ma'am.
Revant, make a note of it, Revant. Manoj Kumar.
Yes, ma'am.
Okay, Dama. Revant, you can wait for 10 more minutes and you can dismiss Rama. Thank you, Revant. Sujitra, thanks a lot. Sujitra, thanks a lot.
I'm not gonna.
Ma'am, can we exit the meeting?
Exit.
Hello.
Yeah, you can exit.
Okay, thank you. My name was noted Manoj Kumar, and I need send any mail ID, or you have my
Can you tell your email ID?
MANOJ
Yeah.
EE.
Sorry. Pardon.
Manoj MANOJ
Okay.
EE
Okay.
2015
Okay.
at gmail.com.
Okay. Thank you.
Thank you.
Hello? Excuse me?
Yeah. Tell
Hello.
me.
Yeah, bro. Bro, in the feedback form, they mentioned that we want to provide a WhatsApp number. I doesn't have a WhatsApp number, so what can I do now? WhatsApp in my phone.
Yeah, it's okay. You can provide your normal number. It need
Yeah, okay.
not to be a WhatsApp.
What, bro? Pardon?
Need not to be a WhatsApp. You can provide your phone number, mobile number.
Yeah, okay, bro. Thank you. Thank you for clarification.
Yes, ma'am.
Shall I stop recording?
Yes, ma'am.